Greetings, the Astro 30 here yet again, and I just cannot help myself. Got some more PCBs here. Now, you're probably wondering what it is. Well, you probably know by the title now, obviously. But I did put a poll a fair few months ago now, I think it was about 6 or 7 months ago, of whether I should revive the old 1977 ETI-480 power amplifier module. So that's exactly what I went and did. I've gone to the trouble of routing a brand new PCB for it, and here it is here. I've put the power output around about 50 watts because that's roughly what it is going to produce. The only changes that I've made from the original circuit and this is they used two 220 ohm resistors, there's one here and one here, in parallel with each other on the original circuit, which makes 110 ohms when they're in parallel. So I changed them to 110 ohms. The reason they used two 220s is because they wanted a half watt 110 ohm, because the original resistors are quarter watts. So I've saved two components that way. The other change is the VBE multiplier is now a BD139 instead of the BC547, I believe it is on the original. I could be wrong. If I'm wrong, there's a caption down the bottom of the screen. Anyhow, so this is going to be a new build. I'm not sure what I'm going to do with it. Now you may be asking yourself, why would I route a PCB to start with without actually testing that the circuit works? Well, I know that the original circuit did actually work, so there's no problem there. All I've got to do is just get one of these PCBs out, that'd be nice. With the changes to the transistor, for instance, that should work without a problem. I don't see any reason why it wouldn't. It's not a transistor where its HFE has to really matter. It's only a VBE multiplier. So if I could get one of the PCBs out to look at it properly, it'd be great. So I've gone and got my customary 5 PCBs made. They do not want to come out the bag. Oh man, there we go, finally. And there it is there. Now I've made it so you can use a metal bracket at the top, angle bracket, to mount it to the heatsink, or get a heatsink that already has an angle bracket on it. And yeah, I've checked all the layout several times. I've used really thick copper traces, especially on the power supply rails, just well because I could. Plus it makes the longevity of the amplifier better because it can handle more current through the traces that are thicker, and which means, because when current passes through the copper traces, they will get hot on their own. Let's just be real about that and face that. So the larger they are, the more current they can handle and the less heat they'll generate on their own. So as we can see up here where the bracket mounts, there is no traces up here. So the bracket would mount on the top side of the board, not the bottom side of the board, obviously. And I think there's enough clearance here between that trace and the screw holes. They'd want to be. I mean, I could always use nylon screws to pass through the transistors if I really wanted to. But that's the board there. I've left all the original transistors as BC557s and 547s respectively. I think actually, no, there's only 3 BC557s, there's no 47. The 47 was the VBE multiplier. So I've left the original transistors as they were on the original design, and there's not much else that's been changed. It's just a modern PCB layout to it. So there we go, there it is there. So what we're going to do now is just build it and test it and see if it works. But before I do that, I've got to wait for a piece of aluminium to turn up that's in, I think it's 30 by 30 angled. It still hasn't turned up yet. So I'm still waiting for that. So in the next course of a couple of weeks, which will only be about a few seconds for you, we'll get to building this. Never mind actually, I got a second package today with that PCB box. I believe, by the feels of things, this is actually the aluminium bracket. I thought it was maybe something else. So let's see if I am right. So the camera just moved in. Get out of there. There we go. Well, I don't know. Let's get this open. It's certainly covered in enough bubble wrap. Ah, there we go. It just looks weird when it's in its packaging. That's the aluminium bracket I was talking about. All we do is cut a section off as long as the board. This is 300 millimeters long. It's very rough cut on this edge. I don't think it's 30, I think it's actually 25 millimeters by 25 by 3 millimeters thick. So it's, I don't know, it's close to 30 if you include the 3 millimeters. Yep, 30 by 30 by 3, yeah. So that's the heatsink bracket adapter, whatever you want to call it. So I'm glad to see that now. That's so cool. Okay, and for those of you that have never seen the ETI-480 original schematic, here it is here as printed in 1977, the March issue. It's probably not one of their best designs, but it was their most popular. They did have other better designs than this, but this still has merit. Input comes over here through the 4.7 microfarad capacitor and 1K5 stopper resistor that stops any RF frequencies being amplified by the long tail pair here due to long cable runs. We have a constant current source up here for the long tail pair. The ground for the input can be taken either through this COM input, which goes through this 10 ohm ground loop break resistor, which just connects directly to the 0 volt rail, or you can take it out the 0 volt rail. And part of the negative feedback circuitry also uses this ground loop break resistor. Now with the negative feedback, that's comprised of this 10k resistor and 220 ohm resistor. Now this is in the 50 watt version. For the 100 watt version, there's a note over here that the fuses have to be 3 amp and R8 needs to be 4.7k. So with those figures in mind, that makes it a gain of 22.3 for the 100 watt version. They state it's a 100 watt version because they have added an extra pair of output transistors. In reality, it does allow you to move more current, but it doesn't necessarily mean you'll get any more output power out of it. Because the supply rails are only plus minus 40 volt in the original version and plus 35 volt for the updated version. This was sold as a kit back in the day by Dick Smith Electronics and JK Electronics in its original form, and I've built countless modules of these. It's a common collector output stage. From the driver's perspective here, we're actually configured as C-Clay output pair, compound pair. The only changes I made from this circuit was these two 220 ohm resistors are now 110 ohm respectively. They had two in parallel to make it 110 half watt, because these were originally quarter watt resistors. The other change I made was, as I've said, I've changed Q6 here, which is a BC549, to a BD139, so it can be mounted directly to the heatsink. And this 470 ohm variable resistor is changed to a 500 ohm, and we would use that to set the quiescent current of this amplifier to around 35 mA, which is what it says over here. So that's their original schematic. There's only been a couple of changes, as I've said. And for clarity, here is my redrawn schematic. It follows the original basically to the letter, just with the reflected changes like the BD139 transistor here. I'm using TIP2955 and TIP3055 transistors respectively instead of the original 2N ETI-480s and MJ-2955s, because they're TO3 devices. They're also pretty much now obsolete anyway. So that's it. That's the schematic for the power amp, and I've also added a couple of bulk filter capacitors here, 100 microfarads, 63 volt. Anyhow, so what we should do now is probably build the thing and test to see if it works. I'm pretty sure it does. Alright, I got most of the parts I need to build this except for the 100 nanofarad capacitors, because J-Card didn't have any. So what I've gone and done is I've ordered some online, about 20 of them, from another seller. So what I'm going to start with now first is I'm going to start mounting all the low profile components like resistors. I'm going to start with these 110 ohm resistors, and then I'm just going to go from there. So I'm not going to take much footage of this, just bits and pieces across the way, because, well, doing time-lapse videos is a lot of processing time and editing time, which I don't want to really have to go through the hassle of doing. So I'm going to get on with assembling this PCB, and we'll come back in certain periods of time along the way just to see how we're going. I also do not have the output stage transistors. I've got everything to build up this part here, just not the 100 nanofarad capacitors. Okay, I've got most of the low profile resistors, like the half watt ones, installed. However, I'm missing the 2K7 that goes here because I forgot to buy it. And I don't have any in stock, so yeah, well, that's fine, I guess. I'll just buy them next week when I buy the output stage transistors. Next thing I'm going to do is I'm going to install this Xeno diode when I can find where it's gone. And indeed it is an 1N4734, which is a 1 watt 5.6 volt Xeno diode, which is part of the not the bootstrap, the constant current source on the input stage and on the VBE, not the VBE multiplier, the VAS constant current source transistor. Right, and as this should not be drawing that much current, it should be fine to place it flush with the board. I don't expect this to have more than 5 milliamps running through that circuit anyway. Okay, that's soldered in. Okay, so that's the lonely little diode done, and it is the correct way around, as we can see there. So next I might do the fuse holders, the input connector socket here, which is going to be a JST connector, as well as the spade terminals whilst everything is still flat. The 2K7 I will put in later. It's fine, I can still get access to it. So I need to go find all the hardware that I need to do, well, at least the fuse sockets and the input socket. Right, found a two-way JST connector, which is going to be awfully close to that 100 microfarad capacitor. So I'll just grab the 100 microfarad capacitor and see if I'm going to have any clearance issues with the connector. No, just clears it just fine. See, that's just perfect. So it's tight, but it's fine. So I'll take that back out because I don't need that in there at the moment. See if I can do this without burning myself. Apparently, it probably would have been easier to, you know, like turn it upside down on the desk, but I didn't really want to because, well, I'm lazy. So I'll just do it this way. Now, remember that this socket, it's common, is connected via the 10 ohm resistor to ground. It's not directly connected to ground. So if you've got a preamp connected to this with the same ground as the 0 volt rail, then you would just use the input part of the connector, which actually I've just realised I've soldered that on backwards. Anyway, I'll fix it in a minute. So if you were to run a preamp, you just run the hot wire in and not the ground. So let me fix this connector up because I put it the wrong way around. Okay, so next it'd be a good idea to do these spade connectors, terminals, which are probably going to be awkward. That puts over there. I might do the same trick that I did once before, and that's just like, you know, tack them in from the top. If I can so get soldering iron to do something. In fact, I might do the same for the fuse holders, or fuse clips, because they're the same height. Just got to make sure that these are oriented correctly, otherwise it's the fuse is not going to fit in there. Trust me, I've done that a few times before, soldered them the wrong way around on the board. This is very reminiscent of building the ETI-480 kit, even though it's a completely different circuit board. So I'll just move that to the side, and I can turn this upside down and solder everything properly. There's one more to do, which is the output connector. Alright, that's all those pieces of hardware soldered in now, and everything still looks relatively straight. So now I can pop this back into the jig and continue on assembling. I'm going to go with probably the ceramic capacitors now because they're only a certain height. It's starting to look like a circuit board now. Well, a working circuit board I should say, because it always was a circuit board. But with the components on it, you know, whilst it's being nearly populated, it makes it look like a, you know, working circuit, I suppose. I don't know what I'm talking about right now. Take one of the leads in at least. Right, then I can turn him over and knock it over. Make sure that one's soldered. I will put in the larger transistors, the BD139. Now I've marked on the board here an E for the emitter, so that's on the left of the device, so it goes ECB, or emitter collector base, on these transistors. I will confess that the ETI-480 was where I first learnt about how power amplifiers worked. Like, well, they're discrete counterparts anyway, and then it became obvious when you look at equivalent schematics of integrated circuit power amps. But yeah, this original kit article, whatever you want to call it, was where I first cut my teeth on power amplifiers. The only thing that I'm going to install now today is these 5-watt resistors, which are going to have to be real close to the body where I bend them, because yeah, they cannot be touching each other. Oh, that's got a clearance issue. They'll have to be raised above that 33 ohm resistor there, and we're going to stare at it for a while. No. So I'm going to move on to the next stage, which is getting the rest of the components that I need. I'm also missing a 3 nanofarad 3. I didn't get one of those either. Oh, righto. That's fine. I can get that next week as well when I get the 2K7 resistors. And hopefully by that time my order of the 100 nanofarad capacitors come in, and then I can complete the construction by building the output stage. So whilst I'm waiting for that to happen, it might be a good idea if I now cut the bracket that needs to go across the top of this board to suit said output stage first, and drill all the holes and make sure everything lines up, because I've got to make sure that the metal part of the bracket clears the solder terminal connections here on the top of the board, or else it will short it out. So yeah, that's what I'm going to do now, is cut that out, drill it, and get that ready at least. And then we're almost in the realms of testing this thing. It is so much nicer having a larger desk as the tripod fits on it. Anyway, I've cut the bracket, as we can see here. It's 108 millimeters long. The actual measurements of this is 32 by 32 by 3, so, and 108. I just cut that with a hacksaw and just did it really slowly using a sawhorse clamp, you know, those ones that you put your work in the middle of it and then you turn the handles to clamp it down, one of those things. So I've got here the drilling guide for the said bracket here, and I've calculated it based on measuring the hole centers. Well, it was actually done in the CAD, so I know exactly what the dimensions of this thing is, but just measuring these dimensions, including that way. So this top one here is the transistor mounting face. That's the one that faces up at you, so this is be with the bracket oriented in that sort of fashion. So that's what this line here means. That's just the edge of the material. I decided I was going to come up 15 millimeters for the hole centers for the main power transistors. However, and 6 millimeters for the small BD13914i transistors. However, there would be a little tiny bit of overhang of the BD transistors, a little bit, about 2 millimeters or so. So I've actually written over here 17. So instead of coming up 15, make it 17 for the main transistors, which means that's adding 2 millimeters to that. So that would also mean you'd have to add 2 millimeters to that one, which would make it 8. Anyway, we come in 9, drill a hole, go ahead, 20, drill a hole, go across, 15, drill another hole, 10, drill a hole, 10, drill a hole, another 15, drill another hole here, and finally go 20 and drill another hole here. And this edge should equal also 9 millimeters. It's pretty simple. And down here is the actual heatsink mounting face. So that's the face that bolts up to the heatsink. Excuse the focus there. Again, I've come up 15, but I decided, well, it's 32 millimeters in total width. So why not put it in the center and make it 16 instead of 15? So we do that. And it's 108 long, as I've said. So to start the drilling, I'd mark the center hole at 54 millimeters. Go 20 out for the next hole, 20 out for the next hole, and 20 that way for that hole, and 20 that way for that hole. That way it'll line up on one of those metric heat sinks with the fins that you have to like put screws in between to actually screw into the material. One of these ones. It doesn't necessarily have to be this long. This is 255 millimeters or something, I think it is. 250. You could use a 75 millimeter long one for all that matter. Not 75, 150 I think it is. Whatever size it is. But the idea is that this bracket would mount to the face like that with screws tapped through, which is why I have those measurements. So if we look between the fins, as you can see where those lines are, they line up within the fins, central to the fins. that is the whole entire idea. I mean, some of them you can't see because of the way the lighting is, but that's my method anyway. So that's how it's going to be drilled. I'm still kind of debating whether or not I'm going to use this style of heatsink, but that's the drilling guide for drilling the heatsink bracket, and that's the guide I'm going to follow. So the next thing to do is to drill this so that the transistors can be mounted and the board can be mounted to the heatsink. Alright, so there's the heatsink bracket drilled, including the mounting holes for the heatsink itself. It does need a bit of a clean-up. The holes themselves practically do line up. They may be slightly off. I don't know how well you can see how they're, lined up. But these are drilled out to 3.5, so they should allow enough wiggle room to get everything central. So what I'm going to do is I'm going to put a bunch of these M3 10mm screws and nuts through this bracket and actually screw it to the circuit board just to have a final look. If I have to enlarge these holes to 4mm, I will do so. Yeah, it looks like I might have to enlarge these to 4 because it is a bit tight. These two over this end are fine. It's just these ones are off. But my main concern is making sure that the edge of this bracket does not short against the solder pads, because otherwise, well, it'll short the output stage out. But yeah, it is awfully difficult to get a screw in that side straight. See, it's all bent at an angle. Okay, so I'll drill them out to 4. I'll drill these other two out to 4 as well, just to, make sure there's plenty of, movement here and there. So I'll get to doing that and come back in a second. Yeah, that's a much better fitment. I still had issue with this one screw here, slightly still off. So I ended up just screwing the screw in sideways with the screwdriver, and it basically just reamed out the PCB material, because it's soft anyway, and made the screw fit straight. So that's really a non-issue. But so far it looks like the bracket is clear of the solder pads, albeit like about a mil and a half gap, which is perfect. Yeah, so this doesn't line up too badly with the edges. There's a slight little lip here, but that's neither here nor there. The point is, it's mounted to a bracket. These aren't going to be the final screws because these screws are going to be too short. They have to be 15mm. These 10 ones will probably be alright. The nuts are coming very close contact with that trace, so that's one thing to watch. Unless I use 15mm long screws here and some like nylon insulated washer there, just so that these metal parts are not coming into contact with these collectors, which is the output, because yeah, I don't want to breach the solder mask on here and making contact between the screw and the trace. So that'll be something to do when I come to finally assemble the output stage, which will be the next thing, and then we can work on testing it. Now the other thing is I have got the 100 nanofarad capacitors in there now, because I got my order yesterday actually. I still do not have the 3.3 nanofarad capacitor that goes over here, and I still do not have the 2K7 that goes over here. That will be done very soon. But for now, what I wanted to concentrate on was getting this bracket done. And it was a lot easier than I thought it was going to be. So that's a good thing. But this is what happens with holes going off when you drill with a hand drill. So yeah, it's tight. That screw is at a slight little angle, but overall it's fine. I mean, this PCB material will succumb to the screw when you tighten it, so it's not going to cause any issue. I just got to remember that because all the other screw holes line up almost good, these do in the middle, these two are fine, this one's slightly off and this one's off even more, is that I've got to screw all these 6 in first 1, 2, 3, 4, 5, 6, and then screw the 7th one in last. So yeah, but I think I might use I've got some M4, I believe it is, nylon washers that I can use here. The hole might be a bit big though. I might need to go get M3. That's alright. Yeah, so from a design perspective, this didn't turn out too bad. Okay, I've got the rest of the parts that I need to complete the assembly of this ETI-480 clone. So what I'm going to do is I'm going to mount the capacitor that I didn't have before, plus the resistor, and then I'll mount the output stage transistors. I'll just take one of these screws out at a time, bend the legs over, put them through the hole, do the next one, and the next one, and the next one, and the next one, and the final one before soldering anything, so that way that all the screws are tight, the transistors are flat, and they're not like sitting up at an angle or anything stressing the circuit board or the transistor. So I'm going to get on to doing that, and we'll come back when I've completed that. Okay, shit me in the ass. I've got the wrong size bloody screws. They're 15mm long, yes, but they're M4, not M3. So yeah, they're practically useless for this job, but what I'm going to do is I'm going to use these 20mm long M3 screws. I'll just change them out at a later time, but for now it'll do to get the output transistors mounted, plus I've got 4 of them, so. And that's sort of what I meant. I haven't done the drivers yet, but that's fine. Those screws are way too long. There is just enough leg sticking out the bottom here to solder to, so that makes it just perfect, I reckon. You wouldn't want to use any material any thicker than 3mm, or else you're going to have a hard time soldering these legs. They are not coming into contact with the heatsink bracket, so that's a good thing. And I basically bent them over at right angles around 2mm away from the end of the shank, a little bit that sticks out further than the actual leg itself, so it's 2mm down and then bent over at right angles. You probably saw me doing that just a few moments ago. These isolators are hanging over the edge of the heatsink, but that's perfectly fine. So now I've got to do the drivers, and then we can solder the thing, and then yeah. Oh, and the VBE multiplier, and yeah, we can then go about testing it. So with these TO-126 transistors, I would do the same thing, bend them about 2mm at right angles down from the wider part, so that they line up with the hole properly. Yeah, but this one would have quite a lot more leg sticking through, but yeah, that's what you get. I have noticed an issue with the isolator though, it hangs over the end too much. Now, you could probably get away with trimming a bit off, because these are designed for TO-220s, not 126s. So you've got a fair amount of material to play with there before the actual metal part comes into contact with whatever you're trying to isolate. So if you trimmed off, say, about 3mm off the end of that, that should be pretty fine, because otherwise it'll bend over at right angles and look a little bit strange. That's about all you should need. Yeah, that will fit a lot better. So I'll just put my transistor back in and the screw, etc., and continue on down the line until I've got all the transistors mounted. I also had a good idea of how to insulate that nut away from that tray, since I just took one of the bushings and I cut the end off. That'll work as an isolated washer just nicely. And yeah, I'm using the 20mm screws on these ones too, because the 10s are a little bit too short with the extra bushing there. I will change them to 15 again at a later date. For now I just want to get this built and tested, and then I'll worry about, you know, screws later. So I'll just tighten him up. There we go, perfect. And now that nut is isolated from this trace. Right, continuing on. Okay, I'm ready to solder. I've nearly used this whole entire roll of solder that Danish Dark gave me, but that's okay. It may take a little bit more heat now because it's mounted to a piece of aluminium, but that's fine. Make sure you put the right transistor in the right holes, or else it could literally self-destruct. Alright, that is the construction complete on this. Everything's now soldered in, screwed down, everything's in the right place, everything's isolated. Next thing to do would be to test it. Before I do that, it might be a good idea to make sure that all these transistors collectors are isolated from the bracket, because otherwise it'll cause a problem. Okie dokie. Appears to be okay. Beauty. I mean, the main output transistors doesn't really matter if it's not isolated from the bracket. However, if the bracket comes into contact with ground and the case is grounded to the power supply, well, it's going to short the output stage out. So that's now ready for testing. Okay, so here's the setup. I've got two 100 ohm resistors across each fuse holder with the fuse removed. They're safety resistors. The bracket is just vice gripped to a handy little heatsink that's just lying around. I've got the toroidal transformer hooked up to the AEL-480 power supply. Seems fitting. Plus it already has the lead made for that base buddy, which suits this module just fine. I haven't connected the ground connection yet, which might be a good idea. And I've got the dim bulb set up just there, just in case there's a problem with either the transformer or the circuit. I'm not going to blow any fuses, etc. The multimeter is hooked up across one of the 100 ohm resistors to measure the voltage drop, and for 35 MA we're looking for 3.5 volt. The ground connection. Now it's not put into a dummy load and there's no input signal for this test. Okay, so I'm going to turn the dim bulb on. Nothing unusual, and currently we've got 0.996, almost a volt there. We need a little bit more than that, so I need to find a screwdriver, and I'll just quickly check nothing's getting hot. I'll see if I can actually increase the bias. Yes, I can. So we need 3.5 volt. Multi-term pot is very handy here. Okay, that's a bit too much. Back it off just a tad. I'm going to say there is about right. So all I need to do is just let it sit for a few minutes to stabilise, and then readjust as necessary. So you can actually check the voltage drop across the, I'm just peeling transistors here, the other resistor, just to verify the reading. It doesn't really matter which resistor you use. And as we can see, there's going to be a slight discrepancy between the two resistors because of tolerance of the component. These are 20% tolerance components. So I'll leave that sit. Dim bulb is currently not glowing much at all, so it's pretty much safe to assume it can be plugged directly into the wall. Alright, so it's been sitting a few minutes. I'm going to assume, for all intents and purposes, that the bias is right. I'm not going to adjust it any further. So next thing to do with testing a power amp is, first I'm going to turn it off, is to verify what voltage is coming out of the output, like its DC offset. So one leg goes to ground, the other one goes to the output connection. And I'm going to turn the dim bulb back on. That is perfectly acceptable. That's only like 21 millivolt DC offset. I'm not sure what the original circuit was, but I'm pretty sure it was pretty close to that. So with a little bit of circuit modification and messing around with, say, the collector resistor of the first input transistor, you could adjust that DC offset a bit. Playing with the negative feedback components will also help with DC offset. It's just basically balancing the input transistors to get as 0 volt possible. But currently I'm quite happy that is working. So what I'm going to do now is I'm going to set up the oscilloscope, dummy load and an input signal and see if this is actually working as an amplifier. So for now these can come off because they're no longer needed. I can put the fuses back in. They're not even warm, by the way. Another fuse. Alright, I'm going to get set up for the next test. Alright, got everything set up now. I've got the 10 times oscilloscope probe, dummy load. I'm using the little oscillator off here because the output's 600 millivolts, 550 millivolts, whatever it is, peak to peak, which is much more controllable than what comes off of the oscilloscope directly. It'd probably be too much to go into there, it'd probably overdrive it. Dim bulb is gone, so alright, let's plug it in and see if we have an output. We do, but it looks weird as hell. It appears to be ringing for some reason. It's not a pure sine wave and I'm not really sure what's going on there. Alright. That's maximum output, which is 22.5 volt peak to peak, so it's yeah, it's not very powerful. Yeah, I'm not sure what that ringing is. It looks like it's oscillating. Yeah, that ringing is kind of concerning because it shouldn't really be doing that. And the heatsink bracket is getting quite hot, so I might just... Oh, wait a minute. It's 63.1 volt peak to peak out. Right, okay. Okay, so it's approximately 63 volt peak to peak. Divide that by 2, multiplied. That by itself, divided by my load, is 124 watts peak. So 63 divided by 2, divided by, multiplied by 0.707 to give me the RMS. 22.2, 22.2705 equals that, divided by the load, easily 61 watts RMS. However, that's dissipating quite a bit of heat. So I might actually kill the signal gen and see if that cools down. Yeah, the transistors are starting to cool off. Bracket's still quite hot though, but it is cooling off. That'd probably be because of that ringing oscillation. I'm not sure why it's oscillating like that. I don't know, but that might be an issue. There's a 100 nanofarad capacitor missing off the circuit board down there. Might help if I actually put that in. That was kind of a brain fart, but anyway, I don't know how I missed that one. I believe that's all the capacitors now soldered in, so let's try for a second test. So I'll plug him in, maybe. That actually looks a lot better, to be honest. Yeah, that is much better. Yeah, it helps to have the stabilization component in there. I'm not sure what capacitor that was. I think that's going across one of the 110 ohm resistors. So it's kind of vital, but that looks a lot more healthier. Just need to keep an eye on the heat. Turn it down. Still pushing 63 volt peak to peak out, that's fine. So currently we're pushing almost a volt out. So that should not get as red hot as it was, because, well, basically the positive going side, which is this side, was oscillating, which is what the ringing was. But yeah, they're getting warm. I mean, this is not a real adequate heatsink solution, but it is better than not having a heatsink. Never test a power amplifier without a heatsink. So I'm going to let this run for a minute or two, and then I'm going to come back and check the heat, and then I'm going to put it into a speaker and see what it actually sounds like. I might do a frequency response test first. Now, it's been running a couple of minutes and it's not overheating. It's warm, yes, and it's dissipating into the load okay. I will do a 4 ohm load test in a minute. However, I want to do a quick and dirty frequency response test, so I've got it set here so it's roughly within these two graticules. So I'll turn this right down, and we're not experiencing much roll off, and we're now at 146 Hertz. So I'll go to the 10 Hertz. Yeah, that looks like absolute arse. So what are we at? 7.5 Hertz. We're at 10 Hertz. $11. Signal starting to correct around about the 20 Hertz mark. So currently, yeah, I'm going to say it's 20 Hertz at the low end. So I'll just quickly check the top end. Okay, we're at 3 kilohertz. 4, 5, 7, 8, 16, 20, 27, it's rolling off, yes. It's good up to around about the 11-12 Hertz mark before it starts to roll off a bit. That's fine. Okay, so we know that this is a pretty good frequency response. Put that back to 1 kilohertz roughly. Right, so we know it's a reasonably good frequency response. Alright, I'm going to test what the power is into 4 ohms now. I bought about 4 of these 4 ohm, well not about, I did buy 4 of these 4 ohm 100 watt resistors, because I was going to build another dummy load, but I haven't got around to it. That was a couple of months ago that I bought these. So what I'm going to do is I'm going to swap out my 8 ohm load for the 4 ohm load. We're going to get probably a little bit more power out of it, but yeah, not much. Now I've got to be careful that these don't short onto the aluminium here, because that'll short the output, and there's no output short circuit protection. So right, we plug it in. We still have a signal, although it was moving around a bit, but it's stabilised now. So what I need to do is I need to turn my volts per division down, turn the amplitude up. Okay, we're actually pushing a little less. We're pushing about 58.2 volt peak to peak. Okay, so 58.2 divided by 2 is that multiplied by itself, which is roughly what we had before, divided by 4. Now it gives us 211 watt peak. So 58.2 divided by 2 multiplied by 0.707 to give us the RMS. I mean, I can read it off the oscilloscope, but I don't see the point because I'm standing here right now. 5737 equals that divided by 4 ohms. You're looking at about 100 watts into 4 ohms, which is probably about 20% extra power compared to 8, because 8 RMS is about 60. It lives up to its original expectations of the original designer. These things probably getting a little bit warmer. It's probably going to operate a little bit better because it's on a better designed PCB. However, we know that that is functioning, so what I should do now is hook it up to a speaker, source of music, and see what it sounds like. Alright, got a speaker hooked up. I should probably plug it in. There's a bit of mains hum there, that's only because of the way it's grounded. It actually sounds pretty good. The camera won't do it justice, obviously. Last thing I want to know with this thing is what its input sensitivity for its full output is. So I'm going to have to set up the dummy load again, etc., and take that measurement before we close this one out. Alright, dummy load set up. I've got my oscillator hooked to the input. Now it looks like there's a little bit of DC offset coming off of this little oscillator, so I put a capacitor in series with the input because it's not measuring on the scope correctly. So I'll plug it in, and it looks like we have an output. That was my phone. So I'll crank it up until I clip. Something's wrong with the output power. Right, I was having an issue before because of the grounding of the scope was giving me a invalid measurement. So I'm using the small scope to measure what the input frequency is, or the input voltage, I should say. So I plug it back in. We have an output. The input didn't drop much. Okay, so I'll turn that down a bit, and now I'll up the amplitude till it clips. Alright, we're clipping there. Back it off. Now this is in times 10, but it's 3.24 volt peak to peak for full output. So that's all I wanted to know. So I'm quite happy how that turned out. It's working. For all intents and purposes, working perfectly. The design could be improved, yes, but for how it was originally designed in the 70s, almost, well, the same age as me, but 1 month older. Yes, a 46-year-old power amplifier it works fine for what it's designed for. It doesn't push the full 100 watts into 8 ohms as they claim. It's something like about 200 watts into 4 ohms, I believe it was what it said. They were taking the peak measurements rather than the RMS values, but they reckon it was RMS. Back then in the 70s, people lied. So anyway, that's all I've got to present with this. $70 worth of components, about $20 for a piece of aluminium stock. So yeah, nearly $100 just to build this amplifier. Was it worth it? Yeah. What am I going to do with it? Bugger if I know. I'll find something for it. Anyway, I'm going to end this video here, and if you enjoyed it, please remember to rate, comment and subscribe below. And you can always follow me on Facebook, and the links for all that are in the description as usual. I'll also put a link in the description to the PCB file from PCBWay, so you can order a PCB if you want to build it. But other than that, that's all I got for you. Anyway, thanks for watching. Cheers, bye.